Good morning from the Sydney. I'm truly proud to be presenting in front of a group of highly esteemed individuals, including many academic colleagues from various universities. The three major areas within the Earth observation industry are natural science, space science, and computer science. My previous presenters covered the basics of the first two areas, and now I will be discussing how computer science helps in analyzing remote sensing data. In the context of sensor data, the process of turning raw data into actionable decisions requires a specialized approach due to the nature and volume of sensor outputs. The key steps include data acquisition, data transmission and storage, data processing and cleaning, data analysis and feature extraction, modeling and prediction, and finally, we can get decision making. Now I'm going to discuss about, first of all, I'll discuss about the challenges of big data, including data complexity and types of resolution. After that, I will provide some overview of artificial intelligence with various methods. And at the same time, I will also discuss about the components and classification of machine learning algorithms, including decision tree, random forest, and artificial intelligence neural network methods. I will also discuss about the remote sensing digital image processing systems with some examples outcome of the analysis. And finally, I will give you some conclusion and with key challenges. Okay, now let's check out about the key challenges. Okay, so basically remote sensing generates huge amount of data sets. Okay, for example, satellite images, multispectral data, and so on. And just I'm giving an example from the NASA. NASA was actually generate 12.1 terabyte data of every day from thousands of sensors and systems. And at the same time, NASA upgrades its spacecraft to handle much faster and larger data transmission by a factor of 1,000 using optical laser. Some missions could generate as much as 24 terabyte data in a single day. So, increasing these volumes of data not only challenge, there is other challenges such as transferring data, how we can search data, how we can store data effectively, how we can process, how we can get real-time decision-making, and many more are actually getting exponentially increased. Top of these, algorithms and instruments growing complexity. Okay. Rate of increment of technology, refresh and declining budget environment, all are these significant to big data. Now, soil health monitoring at these large scale requires processing vast amount of data to extract useful information. Now let's check out about data complexity. So in remote sensing, the image resolution refers to the amount of information available in satellite imagery. There are 4 types of resolutions in satellite imagery. First one is spatial resolution. Second one is spectral resolution. Third one is radiometric resolution. Fourth one is temporal resolutions. So these 4 types of resolutions determine the amount and quality of information in an imagery system. Now let's check out about what is spatial resolution. So it is an image refers to the size of the smallest unit of an image that can be resolved on the ground, and in digital imagery is limited by its pixel size. So there is 3 types of spatial resolution. Number 1 is high spatial resolution. Its range is 0.41 to 4 meter. Second one is medium spatial resolution. Its range is 10 meter to 30 meter. Third one is low spatial resolution. Its range is 30 meter to 1000 meter. Check out about this example. Have a look here. This is a land surface. Okay. Check out this one. The pixel size is 1 kilometer square meter. So in this image, in this pixel size, this is 1 pixel. We can't see anything. Okay. Check out this, the pixel size where 250 square meter. Now, at least we can find there is some areas covers forest. Here you can see urban areas, these are water, and then others again. Let's check out about some examples from video.
Shop Black Friday hot deals like 20% off no-go, only at Super Cheap Auto, and Sunday.
The term spatial resolution implies what is the smallest object that the sensor will detect on ground. It does not actually translate into whether the smallest object will be recognizable. It only means what is the smallest size which a single pixel in the sensor covers on ground. So now just imagine a football ground, which is rather, let's say, 100 meters by 100 meters in size. If the resolution of your satellite sensor is 100 meters, this entire playground will be detected as a single pixel. It means that you can no longer clearly see, or rather no longer see anything else in the playground. Imagine now you have through advancement of technology, increased the spatial resolution from 100 meters to 10 meters. In very simple terms, what it means is the same playground would now be detected and recorded in approximately 100 pixels. So each pixel is covering a smaller area and hence more details. Today, we have civilian satellites which can give you data at 0.5 meter resolution. Though this resolution is not going to result in you and I being recognized by a civilian remote sensing satellite, it surely means that your car or your two-wheeler can easily be detected.
Okay, I think now it is very clear about the spatial resolution. Let's check out about spectral resolution. There is 3 types of spectral resolution. First one is monospectral, second one is multispectral, and third one is hyperspectral. So monospectral resolution is the imaginaries that captured by using a single band of electromagnetic spectrum. When it is multispectral, that means it refers to a spectrum width of few to several hundreds nanometers. And hyperspectral refers to a spectral width of a few to dozens of nanometer, and ultra high spectrum mainly refers to a spectrum width of 1 nanometer or finer scales. I think you can also check out about the another video with spectral resolution.
JB Hi-Fi's Black Friday Blitz is on now with stores open till 10 p.m. tomorrow. Get 40% off the Samsung 75-inch TV. That's nuts. Falcon 55-inch, $378. And this Hisense 75-inch TV thrown out, $944. JB, you've done it again.
When we see the world around us every day, we are able to recognize most of the things by their color. This is because our eyes can sense the reflected light from any given object and can get a rough idea of the material and composition of the object. However, our perception is limited to what meets the eye. To truly unravel the depths of our world, we must see the world through a different lens, and that is hyperspectral imaging. Hyperspectral imaging is a transformative technology that unveils the intricate behavior of light and gives us hidden, useful information about our world. To understand hyperspectral imaging, you first need to understand how traditional cameras work. Traditional color cameras are similar to our eyes. Their sensors capture only 3 primary colors of light: red, green, and blue. And therefore what we see is the combined value of these 3 wavelengths. The next step is multispectral imaging, where we can get 10 to 20 wavelengths of light, having more information than a normal RGB image. But hyperspectral sensors go beyond this limitation, dividing the light spectrum into hundreds of numerous narrow and contiguous bands, capturing detailed information from visible to short-wave infrared spectrum. Each pixel in a hyperspectral image contains a spectrum of information, revealing the unique fingerprint of the materials or objects within the scene. It can also be called the reflectance spectrum, and by analyzing these spectral signatures, scientists can discern subtle differences that elude our naked eye, unlocking a wealth of information about our environment. One of the greatest benefits of hyperspectral imaging lies in its ability to improve our agriculture industry. By analyzing the reflected light from crops across multiple wavelengths, we can detect stressed crops, identify nutrient deficiencies, and optimize resource allocation, ensuring food security and minimizing the ecological impact of farming practices.
I think that's it. I think it is very clear now about the multispectral, hyperspectral resolutions. Now let's check out about the radiometric resolution. It actually describes its ability to discriminate very slight differences in energy, which is expressed as the number of bits for each band. Basically, 8-bit data was common in remote sensed data. Newer version of sensor, for example, Landsat 8 using 16-bit of data product. Let's check out about temporal resolution. This temporal resolution specifies the length of time it will take for the satellite to be able to image the same area again. There is 3 types of temporal resolution. First one is high temporal resolution. The data is actually captured the length of day, like time, which is 24 hours to 3 days. Medium temporal resolution, its range is 4 days to 16 days. And low temporal resolutions, which is more than 16 days. Okay, let's check out about artificial intelligence. Okay, so basically, artificial intelligence refers to the simulation of human intelligence in machines that are programmed to think, learn, and problem solve like human. Basically, human actually has got intelligence, and this intelligence is actually transformed to the machine. So that is basically the artificial intelligence. And artificial intelligence can perform tasks typically which require human intelligence. Okay, that means humans, that means we actually transform our intelligence to the machine. For example, natural language, recognizing patterns, making decisions, and adapting new situations. It also operates through different algorithms, machine learning models, neural network, and other computational techniques as well. Let's check out about different methods of artificial intelligence technologies. Number 1 is machine learning, which is a subset of AI that involves algorithm to learn from data and improve over time without being explicitly programmed. Second one is natural language processing. It actually enables machine to understand, interpret, and generate human language. And robotics, I think you already know about what robotic can do. So basically, robotic uses artificial intelligence to enable machines to interact with their environment and perform physical tasks automatically. Let's check out about this image. So this figure actually showing machine learning relationships with some other concepts of data science and of deep learning as well. So machine learning relationships, so basically data mining uses statistics to extract hidden information, that means pattern, from raw data. However, machine learning as a subset of computer science and artificial intelligence, learns from patterns to predict. Deep learning is one of the main technologies of machine learning and artificial intelligence. We can say that it is the new generation of machine learning, which characterized by learning by layer, and on each layer, the machine has to learn little more. Let's check out about the components of generic machine learning model. The first step is to collect data. It is very important task because it will determine how good predictive model can be. But data we gathered are in most of the times unstructured, contain lots of noise, or have to take other forms to be useful for our machine learning. So data need to be cleaned and pre-processed. After that, we can begin building our machine learning model. For this, we actually need to start by the feature engineering, in which we choose the most relevant features from data. Then we try to select the best machine learning algorithm for the problem. It is imperative in getting the best possible result. The next step is training. In this step, we use a part of our data to incrementally improve machine learning ability to predict. Once training is complete, it is time to test the model and observe how it can perform, how it actually perform against the other part of the data unseen. The performance evaluation is measured by various parameters, like accuracy, precision, and recall. Sometimes it is also required to go back and improve training, then test again. The last step is the result given in the machine learning, and it can be prediction of inference. Let's check out about the classification of machine learning. So you can also check out, there is 4 types of machine learning: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So supervised learning is the machine learning task that assumes a function from the labeled training data. That means when we use supervised learning, we actually need to have our hypothesis, okay? And when we use unsupervised learning, so that means data is not actually labeled. That means we do not have hypothesis. Once we have done our analysis, then we can, after analysis, we can get our hypothesis. Semi-supervised learning is the combination of supervised learning and then unsupervised learning. That means it is a merger of labeled and unlabeled data. In reinforcements learning, the software agent gathers from the interaction with the environment to take action that would maximize reward. Okay, I will discuss some of the methods from supervised learning. For example, decision tree, and then neural network. Okay, check out the decision tree. So here you can see there is a root node, and then we actually need to categorize one concept. Okay, so for example, we can just think about, like, in the university, students is one concept. Okay, so we will have different types of student. For example, undergraduate student, we can categorize the student as undergraduate student and then postgraduate student. Okay, again, we can categorize this undergraduate student to local student and international student. Okay, so in this way, we actually need to create different categories. Okay, let's check out about the random forest example classification. So have a look here. So here you can see the training data, and this random forest is nothing but many, like, as we like, many trees is actually required to get our analysis. That means we can have a look here. This class A, all of these are class A, but check out the data is actually using from F1 and then F2. This one is using F2 and F3. This one is actually using F1 and F2, F4. And in this way, we can actually have n times of classes. Okay, so according to our requirement, until we satisfy, we actually need to have our, we can set out our trees, how many trees we actually are going to use. Until we satisfy our result, then we can keep going, and then we can also train the data again. So finally, we actually get the output from the class. So that means this is the refined output. Okay. Okay, let's check out about the another example, which is artificial neural network. Have a look here. So in this layer, you can see we have input layer and then output layer, and in between, you can see there is a hidden layer, and this hidden layer actually use mathematical function. Okay. The output layer produce the final prediction or classification. Let's check out about different useful classes of remote sensing. Okay. Support, there is a classification which is also support vector machine. And okay, so here we can actually see there is a research has been done, and then and it actually find that the random forest method actually provided the accurate results, okay, for to estimate soil salinity. So basically, random forest handle high dimension and large data sets with many features and capture complex nonlinear relationships between the features and the target variables. So why we actually need to use random forest algorithm? Basically, it actually requires less training time as compared to the other algorithms. It also predicts output with high accuracy, even for the large dataset it runs effectively. It also maintains accuracy when a large proportion of data is missing. Okay, let's check out about data processing. Okay, just say I'm going to remove this anyway. So basically, digital image processing is the subset of electronic domain. Okay, and image is actually converted into an array of small integers. That means pixel, and the pixels represent a physical quantity such as scene radiance, and it is also stored in digital memory and processed by computer or other hardware. Remote sensing, digital image processing system actually refers to the analysis, processing, and disposal of remote sensing digital images through computers to meet the visual, psychological, and other requirements of the technical systems. Image processing is the application of signal processing in the image domain, which is a subclass of signal processing, and it is closely related to computer science and artificial intelligence. There are three basic components of remote sensing digital image processing system are the image digitizer, the computer, and the image display device used to process the image. In their natural form, objects cannot be directly processed by the computer because computer only handle numbers rather than picture. An image must be in digital form before being processed with a computer. Let's check out about this example. Have a look here. Remote sensing image that is represented in the digital matrix. The process of converting ground object information into digital values is called digitization. At each pixel position, the brightness of image is sampled and quantized to obtain a value and corresponding point in the image that represent its brightness level. Let's check out about the pipeline of sensor data and its component. Okay, have a look here. To manage this enormous amount of machine-generated data from sensor communication systems, a distributed data processing pipeline is actually needed for collecting, preprocessing, and storing the data for further analysis. Check out the bottom line is the data collection stage. It actually consumes data from the wide range of sensors with the support of different tools, which is HTTP, MQTT, and then so on. After that, data processing is done in the collection of tools. For example, fume, and others. And next stage is actually storage, which will be done in a database with support for time series operations. Okay, and after that, it actually require distributed data processing, and it also require some other tools as well. And just check out from here, this layer can also consume data directly from this storage in this step as well. Okay, and once we have got data in this layer, we require some tools to visualize our data, and then we can actually get the result from this visualization layer. Okay, have a look here. This is just, I'm not going to show anything from here. There is a link you can download and then extract soil moisture data from Sentinel-1. So this is just an example, okay? And soil moisture retrieval from Sentinel-1. Here you can see some of the codes. And here you can see some of the analysis, some of the analysis, soil moisture retrieval from Sentinel-1 by using Google Earth Engine. Okay, so you can see some codes, and at the same time, we can also print chart. So in the right hand side, we can also find out our chart, and then based on this chart, we can get our result as well. Okay, so in remote sensing, we are mostly interested in measuring the radiation reflected from targets. Features on the Earth's surface react differently in various bands of the spectrum. Spectral reflectance for specific features can be graphed. The individual response of certain features in specific bands is commonly known as spectral reflectance. Here you can see the spectral signature of green vegetation always manifest the peak and valley. That means up and down configuration. The soil curve shows considerably less peak and valley variation in reflectance. That is the factor that influence soil reflectance act over less specific spectral bands. The spectral reflectance of water, probably the most distinctive characteristics, is the energy absorption at near infrared. So here you can see there is a comparison analysis of NDVI, that means vegetation and water index, vegetation index and water index from the Landsat 8, Landsat 8, Sentinel-2, and GF1. Okay, so here we can see indices from different optical data shows that Sentinel-2 NDVI and Sentinel-2 NDWI achieve higher retrieval accuracy. Okay, there is many tools are available. So just I actually put here, you can find out different tools to analyze data. Okay, let's check out about different challenges of data analysis. One of the most challenging aspects for the development of data incentive application has been how to cope with massive and complex dataset effectively, especially in situations in which real-time requirements arise. Sensors provide an unrevealed and unmatched data. To match these needs, as they can provide time-stamped information with enough level of details to characterize observed phenomena adequately. It is very difficult to analyze sensor data due to heterogeneous and complex sensor signals that have varying types, characteristics, and dimension. In addition to this, missing data, noisy data, and corrupted sensor signals can also affect quality of the analysis. And at the same time, high resolution data are very, very expensive. There is a need to balance the trade-off between computational cost and accuracy when processing large-scale and high-dimensional sensor data. Spiral Blue is having the technology at the forefront of this innovation, and Bipul will talk about this in a brief. Okay, that's it. There is some references. Thank you.